Now, when you talk about integral calculus, there are two types of, it's broken down into indefinite and definite integrals. We'll start with the indefinite integrals, and then we'll talk about the definite integrals themselves and show how different they are from each other. So with indefinite integrals, as the name is suggestive, there are no definitions of the parameters of this function. This function doesn't have the limits. Like in terms of the ends, there are no limits, like this is the upper limit, this is the lower limit. There's no specific range within which the curve for the equation is supposed to really rotate. That is under indefinite. But when we come to definite integrals, there are specific limits, within which this particular equation or graph or function is supposed to rotate and swing. Now, there are different methods of integration that are applied. We have the common one, the power rule one. Then we also have the substitution method and the integration by parts. These are the most ones that are used, integration by substitution and by parts. Then once we talk about that, then at a later point, we look at the economic application of the same calculus. Any questions?
No.
No questions now. Let's start with the definite integrals. Now, when you're given a function and you're told to find the antiderivative, by the way, the antiderivative is the same as integration, the antiderivative. And why do we call it the antiderivative? The antiderivative is basically an indefinite. Hello, can you hear me? Hello, can you hear me now? Hello.
Hello. Hello.
Hi.
Sorry, there was a phone call that came through.
Oh, okay. So I was saying, when you talk about antiderivatives, these are basically indefinite integrals. They are represented by this letter, this symbol. This is for antiderivative. And why do we call them antiderivative? It's because they're a reverse of derivatives, okay? They are basically a reverse. I will show you this function. Let's say we have a function y is equal to 2x squared plus 3x, right? We want to find best the derivative, isn't it? Let's differentiate this function. What's the derivative of the function using the power rule?
We have 4x.
Yes, you have 4x.
4x plus 3.
Plus 3, right? This is the dy over dx. Now, what we mean by antiderivative, we mean that you have to reverse this derivative back to the original function. So that is to say, you have to integrate this function so that it gets back to its origin. And the integration is given by this. It is ax to the power n plus 1 divided by n plus 1. That's the integration of that. Plus c, the constant. So it means you have to add 1. You have to add 1 to the power, right? The power that you have, add 1 and divide by that increase. So yeah, basically that's that. We know that we could now begin by rewriting this as 4x to the power 1 plus 3x to the power 0. You know that this is one and the same thing, isn't it?
Yes.
It's just the same stuff. Then we can integrate now so that we can have 4x to the power 1 plus 1 divided by 1 plus 1, right? Plus 3x raised to the degree 0 plus 1 all over 0 plus 1, right? Plus c, the constant. Okay. So when we summarize this, you will have 4x squared plus 3x now, because 0 plus 1 is just basically 1. and the all over 1 all over 2 here, right? That's one and the same thing, isn't it? And then from there, what you're going to do is you're going to divide 2 into 4. It basically that gives you 2x squared plus 3x, which is exactly the original function. You've seen that, right? There is a close relationship between integral calculus and derivative differential calculus. So when you derive the function, then if you want to go back to where it came from, you basically integrate, then it will go back, right? It will go back. And you can keep on doing the rest. Again, from here, if you differentiate, you get back to the derivative. Again, you integrate just like that. That's what we mean when we say it's an antiderivative. Are we good?
Okay, yes. Now,
you have a question?
We are clear. No, I think let's go on now. Ask.
Yeah.
Let's proceed now. Ask.
So now, this is the formula using the power rule. This is the first rule. I think I've already explained this rule, yeah? I've said the integral of a function like this ax to the power dx shall be just, the same x power plus 1 divided by the power plus 1 plus c, the constant. It's the same stuff that we were doing there, isn't it? Are we good? Oh, no. Hello, are we still there? Are we connected?
Yes, we are. There were just some people that came,
Okay.
so yes, I decided to mute. Yes.
Oh, that's fine. Now, the derivative and antiderivatives that deal with the logarithmic functions, the ones that I want us to look at, because those that don't deal with logarithmic functions, they're straightforward. You use power, you just basically add 1 to the power and divide by the increase in the power, isn't it? Not very difficult, yeah? Maybe you want us to do more examples. Can we just have 3 examples, I think? Let's have the first one. So y is equal to, 4x raised to the power 2 plus 3, the constant. Let's find the integral of this, integrate this function. Let's find the integral of this. It will be 4x to the power 3 divided by 3, yeah?
Hello?
Hi.
Okay. No, I understand. I'm getting now.
Okay. Then plus 3 x, we know that this x was to the power 0. So when you add 1 to it, it's just 3x, right? To the divided by 1. You're followed? Yeah. So basically, what we're trying to say is the integral of this sign shall be 4x to the power 2 plus 1 divided by 2 plus 1 plus 3. This is x to the power 0 plus 1 over 0 plus 1, which shall be basically 4x to the power 3 divided by 3 plus 3x, right?
Hello?
As a, hello?
Hello?
Hi.
Okay. Okay. You can go ahead, sir.
Yeah, then plus c, the constant, isn't it? Yeah, you add c, the constant. That's the first example. Second example could be a fraction. You could have 2 over 3 x to the power 2, right? I think let's just write 3. Just write 3 like this. What would be the derivative of this? Plus 5x. This will be what? 3x to the power 3 divided by 3, right? Plus 5x squared divided by 2. Isn't it? Plus c the constant. You're following, right? Yeah.
Hello?
Hi.
The line is breaking. I don't know if it's my network.
No, I'm not speaking. I wasn't speaking. I was quiet. I was
Okay.
trying to think maybe you are not following.
Okay, no. I was following.
Oh, okay.
Hello? Yes.
So 3 into 3, basically, that gives you just x cubed plus 5 over 2 x squared plus c, the constant. This is the derivative of this function. Or the integral, not the derivative, the integral. Okay?
Okay, I'm kindly asking if you may go back to the other example. You deleted, I think. Yes, the one that had 4x.
The one that had y is equal to
is
4x
equal to 4x
squared plus 3. This one.
plus 3. Yes, this one. I was a bit disturbed. Sorry, sir.
Oh, no, it's fine. So I was saying this one, you do the same stuff. You say 4x to the power 2 plus 1 divided by 2 plus 1 plus 3x. We know that this is 3x to the power 0 plus 1 over 0 plus 1 plus c, the constant. So that it can give you 4x to the power 3 divided by 3 plus 3x, divided by 1 plus c, the constant, right? Which is basically the same stuff. You could have 4 over 3 x cubed plus 3x plus c, like this. As the integral. You got it? Very easy stuff. The last example is of a fraction. 2 over 3 x to the power 2 plus, let's just say 5x. It's still the same stuff. Now, quite interesting. Yeah, because we'll say 2 over 3 x to the power 2 plus 1. This divided by 2 plus 1, right? Are you seeing what is happening? Now, this will be treated as a one figure, this one. As one number, the whole fraction. This will be just same stuff. The way how we treated 4 previously. That's how you treat. Okay? So at that level, plus 5x squared all over 2 plus c. And then you will have 2 over 3 divided by, right? If you want, you can write, how do we write divided by? So still everything divided by 3 now. X to the power 3 plus 5x squared over 2 plus c, the constant. Right?
Okay.
We are good.
Sorry. Yes, we are. I want to understand where for example, when we divide, where the 2 is going.
Which 2?
Okay. Remains okay. No, it's fine.
Okay. So now we know that this, for the sake of simplifying stuff, we could just have this lower down, write it down as 2 over 3 divided by 3, isn't it? It's the same stuff. This is just way of illustrating to us. And we know that we could have 2 over 3, 2 over 3 divided by 3 over 1, so that we could have 2 over 3 times 1 over 3. And this just gives us 2 over 9, isn't it? Settled? So
Yes.
we know that this will be equals to 2 over 9 x cubed plus 5 x squared over 2 plus c, isn't it? Yeah. So basically, let's how it is going to become. Yeah, I wanted you to see how to use fractions, and then you will have 2x cubed over 9 plus 5x squared all over 2 plus c the constant. And then you are good.
So, sir,
Okay, Ma?
okay. Unless it's an even number, that's when you can divide. For example, okay. So if it's an odd number, you can't divide. Okay.
No, just leave it like this.
Right.
As a fraction. Okay. And now we go ahead and look at the derivatives and antiderivative that deal with the natural logarithmic functions. So we work with the natural logs now. That was, simple stuff. But let's try to see how we can integrate the logs, the logarithmic functions. How can you do the logs? Listen carefully. If you are given the equation like this, dy over the x, natural log of x is as good as 1 over x. Now you and I know that differential calculus is a reverse of integral calculus, yeah?
You wanted what, sir? No, I'm in class. Thank you. Yes, sir.
It is well. And so I was saying the rule is dy over the x, the natural log of x. In short, the derivative of the natural log of x is 1 over x. And you know that when we are integrating is basically moving the reverse. We're moving the reverse. So if you are given this function, what is its natural log? We want to differentiate that function or to integrate this function, which means integrating this function, you're taking it back to its reverse, yeah? So we know that this function, according to the rule of indices, can still be written as x to the power negative 1, right? So that this is same as 1 over x, isn't it? So what is the integral of this? So if we are to integrate this function, the integral of this function is same as the natural log of x plus c, the constant. It's a rule.
Okay.
However, this rule is only valid if x is greater than 0, not negative. We don't deal with the natural logs that are negative, right? Yes, we don't deal with the natural logs that are negative. That rule, you have to get it. You have not gotten this. Teacher, explain one more time using an example. So if I say, can we integrate the integral of 1 over x? What is the integral of this function? The integral of this function shall equal the natural log of x plus c. That's it. Hear what I mean, eh? or y is equal to 3 over x. Y is equal to 3 over x. What is the derivative of the integral of this? So the integral will be 3 multiplied by, you can take this 3 outside and you have 1 over x, isn't it? It's the same stuff. 3 will be on top. And then you have 3, the natural log of x plus c, like this. You got it?
Yeah. Yes, sir.
You could have another equation, 2 over x. This shall be 2, the natural log of x plus c, the constant. Because this can be written as 2, the integral of 1 of x, like that. That's what we are communicating. That's the message, nothing much.
Yeah, no, it's understood.
Now, we know that we could still work with this antiderivative, and there is what you call the constant rule, which is basically the reverse. This is now when we're dealing with some exponential functions. Some exponential functions. These are rules you need to remember. If you have the derivative a to the power x, because we know that with exponential functions, the numbers, the first is on top. The variables are as raised as powers. These are exponential functions. This is same as the natural log of a, right? Multiplied by the whole function that you're integrating. Okay? For example.
Yeah.
2 to the power x. Those are examples. This can be given as the natural log of what? Of 2, isn't it? The natural log of 2.
Open 1
Open
over
the
x.
bracket.
1 over x.
2 x.
Again.
Yeah, it's the same stuff that we have completed. You see, now?
Okay. Hello?
Hi.
Okay.
So, yeah, that's how you go about these stuff. That's on the constant rule, which is basically the reverse. If you're dealing with the natural logs, obviously it's the same stuff. That would be the reverse. If you deal with the natural log, the answer would just be that. Okay, is the reverse. So what shall be the antiderivative there of the integral of a x? It shall be just a 1 over the natural log of a times a x. Pick this as the formula. These are just formulas. There is no number here.
Yeah.
Yes. So that if we have the integral of 3x, it can be equal to the 1 over the natural log of what? 3 times the 3x. Or 3 to the power x. 3 to the power x. Because you're repeating the whole expression, right? Yeah. Remember these rules. So in short, antiderivatives of exponential function and of the logarithmic functions, you need to go through them and get to find.
I need to go through this.
Now, what if you are given, because the rules are these, we have already said these are exponential function rules. What if now a is equal to exponential function? Let's say there is no a, there is no number. When you say a is equal to e, which means like the constant is equal to 1. You just say the integral of a to the power x. It just gives us the same, right? That's the integral of that. Examples always will do it better. If you're given the integral of 2e to the power x. How do you differentiate, integrate this? Just rewrite this as 2e to the power x, which shall be 2 multiplied by e to the power x, which will be 2e to the power x as the answer, plus c the constant, right? I said you can factor out this constant always. This rule is very important. Whether this is a fraction, you could have 2 over 3 e to the power x. It's still the same stuff. This will be 2 over 3 integral of ex, which will be the same stuff. It will be 2 over 3 a to the power x plus c. You've seen what we mean. That's the application of this rule. Exponential functions, right?
Yes, sir.
Now, what if these are basic rules? Some important integral examples are these. Okay. We want to integrate the integral of, say, x. This is very easy, isn't it? You just add 1. You can use power rule this one. It will be x to the power 1 plus 1. You remember? Over 1 plus 1 plus c, right? Isn't it? So that you can have x squared over 2 plus c. You're followed?
Yes, I'm following, sir.
What if you are using another example, the second one? Now remember we said the integral of 1 over x is equal to the natural log of x plus c, right? What if it is the integral of 1 over x to the power 3? Like the power here is greater than 1. What is the answer? It is wrong to say this is equal to the natural log of x to the power 3. No, you don't do that. Get it? Remember. So you just basically have to rewrite this. This will be x to the power negative 3. First of all, then you start integrating. That's what I mean.
Yes, yes.
Integrate, you add 1 here over negative 3 plus 1, like that. This will be equal to x to the power negative 2 over negative 2, right? isn't it? Hello? Are we good? Are we still connected?
Yes, I think the network is tripping.
You can't hear me now? Can you hear me?
I can get you. Yes, sir.
So this is what is there. You can rewrite this as negative x over 2. Then bring down this, to the power negative 2 like that. But you can still rewrite this as negative half. Then bring this x down squared, right? Because it will lose when you take the whole lot of this down, remember the indices, and take this down, become positive. It will be x squared.
Yes.
So that's the math which is there. Okay? So if you can say 2 over x squared, this can still be rewritten. First, you have to rewrite as 2x to the power negative 2, right? So that you could have 2x to the power negative 2 plus 1 over negative 2 plus 1. That you may have 2x to the power negative 1 over negative 1. And this will give you negative 2x to the power negative 1. That we could easily rewrite as negative 2 over what? X, isn't it? Because we bring this down. That's the message we are communicating. That's another example. Plus see the concept. Okay? You remember I had such parts in the assignment, something like this. Now we are trying to make them clear. We could still have the integral of the square root of x. We know that this can be rewritten as the integral of x to the power half, right? Just rewriting using the rule of x. And from there, you could easily pick it up using power rule. Say x to half plus 1, right? Divided by half plus 1 becomes a bit complicated. Plus c. So now it expands. This will be x to the power half plus 1.
X, which is 2 over 2. Yeah.
Common denominator to 2 into 2.
Which is 1. 1.
Plus 2
No,
times
not
1.
1. Not 1, sir. 1 plus 1 over 2.
Hold on. Let's go back to primary school. What is the common denominator? Common denominator is 2.
Yes.
2 into 2, 1. 1 times 1, 1. Plus 1 into 2, 2. 2 times 1, 2. Right? Then 1 plus 2 is 3 over 2.
Over
That's what
3.
you do. Okay?
Okay.
3 over 2. Even down here, there will be, here there is 1, right? Then there's 3 over 2. It grows big, eh? With integration, stuffs keep on growing.
Yeah.
How do we handle this now? We have to divide this. 1 divided by 3 over 2, right? This can be equal to 1 times 2 over 3, which will just be as good as 2 over 3, right? So that this can be 2 over 3x to the power 3 over 2 plus c. Right. You're following, eh?
Yes, sir.
If you want, you can leave it there. Okay? So which means when you are given, for example, the integral of the fourth root of maybe, you know, x something, you could easily know how to deal with the fourth root. Just rewrite it short. Rewrite. Fourth root will be x to the power 1 over, like that. Work with the roots. Very well. Use those principles you learned previously, previous conversations. Okay? You got it?
Yes, sir.
Yeah.
I'm kindly asking for a few questions that I can go through on my own. Then I forward the answers.
You can try this one. It's the same stuff. Just do it in
okay,
pieces.
I'll try. Okay, I'll try it.
Also this one. You can use it. This is now trying to apply the same stuff. It's nothing much. When you're given a marginal cost, you know how we find the marginal cost from what we learned previously? You differentiate the total cost function, isn't it?
Yes.
Then now, if you want the total cost, what do? You go back, reverse, integrate the marginal cost function. So you have to integrate the marginal cost function. This plus this is fixed cost. So integrate this. When you integrate this, then you'll be fine. Just integrate. This one is fixed because this one is already fixed. Plus the total cost, which means you're just integrating the other part and you create a total cost function. It's not hard.
Okay.
Anyway, we could end here as you wish. So that next time we can look at the definite integrals. All these were indefinite integrals.